Now, as I explained here, just capturing the main steps of an AO system, you have to receive the information from the wavefront sensor. You have to calculate the instantaneous slopes at each of those lens apertures, determine the phase error and reconstruct the shape of the wavefront, and generate DM signals, deformable mirror signals, so as to change the shape of the deformable mirror to instantaneously compensate for the distortion. And that whole system is called an adaptive optic system. So, it has these elements. You have a wavefront sensor which measures the instantaneous wavefronts, and to understand how you use that information of motion of the spots to calculate the slopes, it is easy to understand here. If you think of these as the spot locations, as spots move around, by measuring the instantaneous motion, you can calculate, taking the difference between these two spots, you can calculate the spot slope in this direction, you calculate the difference between these two, you calculate the slope in that direction, combine them to calculate the average slope within that aperture. And similarly, the difference between these two and these two, measure the slope in that direction, combine them to give this average slope in that direction. So, the slope can be split into one slope in this direction and one slope in that direction, and then you can write all this as a set of linear equations in a matrix form, which have to be simultaneously solved to determine the phase. So, what is shown here is the slope, and this matrix is what translates the motion of these spots into slopes by appropriate subtraction, etc. And you write that in a set of as a matrix form. So, we phase matrix here as a vector, and the translation matrix from slope to phase as an A matrix here, which does this translation, and then you invert that to calculate the phase from the slope. So, that is the process of an adaptive optic system. Now, let us see what an adaptive optic system do for an astronomer in reality. So, this, as you can see, is the image of a star formed by a telescope when the light passes through the atmosphere. You can see the image is split up into many tiny blobs of light spread over a large area, and if you take a number of images, you can see that they are all continuously changing. So, at the moment the adaptive optic system is not working, but in a moment when the adaptive optic system turns on, you can see that all that light is now concentrated on a nice airy disk like pattern, which is corresponding to that of a diffraction limit of the telescope. So, earlier the light was spread over a large area as it passes through the atmosphere, and the adaptive optic system compensates for that effect and puts all that light back together into a tight airy disk pattern as shown here. So, that is a simple approach for an adaptive optic system. There are in practice there are various issues one has to deal with. One of the issues is the atmosphere changes very fast. What it means is that you have to do the measurement of the wavefront structure at a rate which is faster than the rate at which the atmosphere changes. This is an expression which we derived in one of the previous slides. This is R0 and this is the average wind velocity. So, if we put this as 10 centimeter, this as about 10 meters per second, you can see that the atmosphere is changing at a time scale of over a few milliseconds. So, which means that the loop of AO system has to be closed at the rate of 1 kilohertz or even more for larger telescopes. Now, within this 1 kilohertz time scale, you need to collect enough photons in each of those spots formed by the wavefront sensor. You can see, you remember the wavefront sensor splits the light from the reference star into many spots, and in each spot you need to have adequate number of photons and measurement accuracy in order to reconstruct the slopes and therefore, the wavefront shape. To do that, you need a bright enough star. So, the chances that you find a really bright star next to any target you want to observe in the sky is very small. We calculated the typical angular size corresponding to R0, which means that is the size angular sails over which you can consider the atmosphere to be the same or the variation introduced by the atmosphere to be correlated. So, you should find a reference star within a patch size of theta 0 as described in one of the previous slides. Now, if you put the numbers in for R0 and typical atmosphere effective heights, you will see that these angular separations are very small. What it means is that for every target you want to study in the sky with adaptive optics, you need to find a very bright star from which you get large number of photons within a very small angular separation, and this is almost impossible. Most of the time you will not be able to find a bright enough star sufficiently close to a random target in the sky you want to study. So, this is a serious problem. Now, how do you overcome this problem? You create artificial guide stars. You create artificial reference stars in the sky. Now, one of the ways of doing it, that is to shoot a laser from the telescope up into the atmosphere. Very often these lasers are based on some kind of sodium transitions. That is because in the atmosphere at a height of about 90 kilometers, there is a very thin layer of sodium. This is naturally occurring in the atmosphere. So, if you shoot a laser which is tuned to a sodium transition, this laser beam will be absorbed by this layer in the atmosphere, and this will become an artificial star there, because that radiation will that becomes a spot where there is fluorescence, and the radiation will travel back from that spot as an artificial star. So, by creating an artificial guide star in the sky approximately the height of 90 kilometers typically where the sodium layer is, you can form a reference object in any direction of the sky. So, you just shoot the laser in the direction in which the telescope is pointing, you have a reference object in that reference star in that direction. So, this is what is illustrated here. This is the Keck telescope which I mentioned earlier, two of them, and you can see the lasers being launched from each of those Keck telescopes, and depending on which direction the telescope is pointing, the lasers get pointed. If both the telescopes are looking at the same direction, they point in the same direction, or they point at different directions in the sky, and they form artificial guide stars, using which you can compensate for the atmospheric introduced turbulence, even if you can't find a bright enough natural reference star sufficiently close your target. So, this is just another illustration of laser beam being projected out of the Keck telescope. One problem with this approach of using an artificial guide star is the following. Any light which is passing through the atmosphere, because the density of the atmosphere changes as a function of height, the light would bend. This is called the refraction of the light as it passes through the atmosphere. Now, if you shoot a laser from the telescope, it will travel through the atmosphere in a curved path and come back through the same path, which means you are not able to measure the overall tip tilt, overall deviation, angular deviation of the laser location, which what it effectively means is that even if the star is here, as far as the telescope is concerned, it will appear as if it is here and it is not changing, its position is not changing, because even if its star position changes to here, the light going up and coming back are following the same path, and from the telescope you will project it as if it is in this location of the sky. So, the overall movement of the star is not measurable with a laser guide star system, which means that you still need a natural guide star for measuring the overall movement of the laser guide star of the overall movement or the tip tilt introduced by the atmosphere, overall movement of the apparent position of the star. But all the higher order corrections, like higher order means everything beyond the overall movement of the star can be corrected by the artificial guide star. So, even in a laser guide star system, you still need a artificial guide star only to correct for the lowest order of the distortion introduced by the atmosphere, which is the overall tip and tilt. Now, there is another limitation when you use a laser guide stars, which is called the cone effect. What it does is the following. This is assume this to be the telescope. Now, if you put a laser at a finite height into the atmosphere, the light from the laser is arriving at the telescope within this cone. However, the light from a distant object in the sky is arriving on the telescope over this entire circular area. So, this entire circular area turbulence is not probed by the laser guide star. The area above the 90 kilometer altitude where the laser is focused, as well as the region which is outside the cone of the laser beam, that is also not probed by the laser guide star, which means that this laser guide star based adaptive optic system cannot work as well as the one where in which you use a natural guide star, which is infinitely far away, and the light from that source exactly tracks the light from your target object. So, this is a limitation. But for small telescopes, this cone effect is negligible, because this cone is almost because this height is large enough, the diameter is small enough, this angle is small enough. So, this cone is almost acceptable. But for example, for an 8 meter class telescope, a sodium laser guide star focused at a height of about 90 kilometers is pretty good. It gives a reasonably good atmospheric compensation. For a smaller telescope like a 3 meter diameter telescope, the laser need not be that high, it can be even 10 kilometers in altitude, and the cone is sufficiently good and sufficiently fills the circular aperture, and the atmospheric compensation can be good enough. But on the other hand, when the telescope apertures become larger and larger, this compensation will not work, and you will need very often multiple guide stars, multiple laser guide stars. I will come to that in a moment. So, with a 3 meter diameter telescope, even with a laser which goes only up to 10 kilometers in height, and using natural guide stars for tip tilt compensation, you can develop a very effective adaptive optic system which works for small telescopes. One such system is called a RoboAO telescope, which is a robotic adaptive optic system which automatically compensates for atmospheric turbulence, and it works very well for small telescopes. On the other hand, when the telescope aperture diameter becomes large enough, this cone angle effect becomes more serious. At that point, you will need to do tomography of the atmosphere using multiple laser guide stars. So, instead of one laser guide star, you use multiple lasers pointed in a region around your target of observation, and using the information coming from these 3 lasers, you combine together that information and do a tomography of the atmosphere, of the net effect of the atmosphere, and then compensate for it. And this is called a multi-conjugate adaptive optic system, because it has multiple often wavefront sensors and often deformable mirrors, all working together, compensating for the effect of the atmosphere, which cannot be probed and compensated correctly with using just a single guide star, single laser guide star and single mirror AO system. And the advantage of this is you can also extend the field of view of your telescope. As earlier mentioned, without a single guide star, you are typically restricted to compensation within an angle of few arc seconds, but here with multiple guide stars you can go to at least 1 or 2 arc minutes in diameter. And this is extremely good for very high resolution spectroscopy and relatively wide field adaptive optics imaging. So, let me just quickly try to quantify in this slide how good your adaptive optics system is. Without atmosphere you should get an airy disk pattern. So, that is your reference. Now, how good is adaptive optics system performing compared to your airy disk pattern? So, if I take an airy disk pattern and measure the full width at half maximum, what is the distance from the center at which the intensity reduces to half its peak value? That is given by 1.03 lambda over d. Now, if I have a AO system, I can compare the full width at half maximum of the image produced by the AO system with that of an ideal AO system or an ideal airy disk pattern would have delivered, and that comparison would give you how good your adaptive system is performing. That is one measure. There is also another issue. When the adaptive optic system collects together the light and focuses it onto a tiny airy disk pattern, it may not able to do that for all of the light. Some of the light will still be lost in the wings of the airy disk pattern. It will not come to the central image spot, and that is measured by what is called the Strel ratio. This is the ratio of the peak intensity of the measured or the AO system delivered image to that of the theoretical maximum given by the diffraction limited image. So, very often in a adaptive optic system, it can happen that 80% of the light is lost, only 20% is collected together and focused to a tiny spot corresponding to the diffraction limit. So, while you are getting your light collected to a tiny spot, you are also losing a large number of photons. You are losing a lot of photons which are lost into the wings of this image, which does not concentrate into the middle, and this leads to a loss of sensitivity of your telescope, and this can be another serious limitation. So, the performance of an adaptive optic system has to be measured both in terms of the angular size of the final delivered image as well as the Strel ratio or the ratio of the peak intensity relative to the ideal peak intensity that can be delivered by a diffraction limited system. So, when you design an adaptive optic system, you will have to decide what you want to do. For example, if you want to do higher resolution imaging, you may be able to say, okay, I do not want a high Strel ratio, but I want all the light to be concentrated as much as possible into a narrow central image or central spot. On the other hand, if you want to detect very faint objects, you want the Strel ratio to be as high as possible. We do not want a lot of light to be lost in the wings of the image, and to be concentrated, not only concentrated in the central image, but also a good fraction of the light should be collected, and that means a very high Strel ratio is also required. So, depending on what kind of science or astronomical observations you want to do, you have to emphasize on whether you want a high Strel ratio or high diffraction limit or a combination of both, and so on and so forth. So, I will come to this point a little later. When you finally what you are trying to define is what is the point source sensitivity you can achieve with your AO system, and compare that with what can be achieved with an ideal system working above the atmosphere, and that would be a good measure of the AO system. So, there are three measures. One is the how tightly the light is brought together into a central focus as close to the diffraction limit as possible, how much of the light is collected in that central spot, and overall finally what is the point source sensitivity delivered by the system as related to the ideal system, which is diffraction limited and is above the atmosphere. Now, if you look at the Strel ratio of the telescope, it can be expressed by e raised to minus sigma phi squared, where sigma phi is the residual wavefront phase aberration. So, this residual wavefront phase aberration squared e raised to minus of that is typically the Strel ratio. Now, depending on how much of the distortions you remove successively, you can improve the Strel ratio, or you can reduce the residual aberrations and you can improve the Strel ratio. So, for example, with the diffraction limited image where no modes are removed, you get an image which is roughly given by d by r 0 raised to 5 by 3, which we previously explained. This is what is the atmosphere limited image residual image aberration. But if you remove just the tip tilt, the overall tip and tilt, that image residual aberration immediately reduces to 0.134 instead of 1 here. And similarly, as you remove higher and higher order aberrations, you end up getting smaller and smaller residual aberrations, and when you plug in that smaller residual aberration in this power here, you get better and better Strel ratios. So, when you design a telescope system, you have to figure out what kind of Strel ratio you want to achieve, and that would define at what level you need to remove the atmospheric distortion, atmospheric introduced distortions from the wavefront which is arriving on the telescope. In addition to the errors introduced by the atmosphere, realistically speaking, the Strel ratio is not just the result of the phase structure function due to the atmosphere alone, but it can be this phase residual can be the result of a large number of errors in your measurement. So, no measurement system is ideal. So, when you measure using your wavefront sensor and compensates for with your deformable mirror, that itself is not ideally working. It has this large number of errors introduced by this. So, in reality, the net error which you are measuring and which actually leads to the final Strel ratio you can achieve is the result of a large number of contributors. For example, how far your laser guide star is from your science target, how quickly you are measuring and compensating for the atmospheric distortion, what is the error introduced by the wavefront sensor because it is collecting only a finite number of photons, and the wavefront sensor measuring system has its own read noise and other noise sources. And then finally, how well are you fitting your wavefront from all the measurements and to recreating the wavefront. All these sources add up to your measurement error and leads to your net residual measurement error, and that finally defines what kind of Strel ratio you can achieve. So, now why this adaptive optics compensation system is important for a very large telescope. The reason is, if you want to, as we discussed earlier, one of the reasons why we want to make large telescopes is to look at very faint objects, which means that the telescope has to be very sensitive. A sensitive telescope can detect objects which are very faint. Now, I define sensitivity here as the inverse of the time needed to reach a desired signal to noise ratio. So, signal to noise ratio defines how accurately you are measuring. To achieve a desired signal to noise ratio, how many photons you need to collect, and to collect that many photons you need a certain time of exposure or certain duration over which you need to collect light from that object. So, inverse of that time is defined as the sensitivity. So, this is the larger the time you need, the less sensitive your telescope is. The shorter time you need to reach a specific signal to noise ratio, the better sensitive your telescope is. Now, you can show that the sensitivity of the telescope scales like the Strel ratio, and just ignore these parameters here for the time being. But if you reduce these parameters and the d dependence etcetera, you will be easily able to see that the sensitivity of the telescope scales like d to the 4, the diameter of the telescope raised to 4 so, what it means is that if I have a telescope of diameter 1, you get a certain sensitivity. If I increase the telescope diameter by factor of 2, a 2 meter diameter telescope with an adaptive optic system, it is 2 raised to 4, 16 times more sensitive than a 1 meter diameter telescope. So, that is why adaptive optic system is very important for large telescopes, because as the telescope diameter becomes large, this factor which grows like d to the 4 becomes very dominant, which means your telescopes become super sensitive when enabled with a powerful adaptive optic system. Of course, in addition to improving the sensitivity, a large telescope also improves the angular diameter. So, if a adaptive optic system delivers an image which is corresponding in size to angular size of the diffraction limiter delivered by the telescope, which is inversely proportional to d, that also increases. So, adaptive optic system work both ways. It improves the sensitivity of the telescope, which means how faint a target the telescope can see. It also improves the diffraction limit or how fine details a telescope can see. Both ways adaptive optic system is enormously important for large telescopes. So, here is a slide which kind of highlights what an adaptive optic system can do. This is a region of the sky here. Without an adaptive optic system, you can see how how spread out the images are, and once you turn on the adaptive optic system, you can see how fine structures you can see here. You can watch the inset. These stars which are so big, now when the adaptive optic system start working, you can see how this entire blob of light which is spread by the atmosphere splits up into tiny objects in the sky. So, there are so many objects in the sky in that region here which you are not able to see without an adaptive optic system. The adaptive optic system allows you to see these fine details. Similarly, here without an adaptive optic system, the image of Jupiter looks so washed out, you do not see any fine features. Here you can see exquisite features on the surface of that Jupiter. And another planetary image, the image of a moon, surface of the moon, you can see how adaptive optic system improves the details you can see on the surface. And this here is the holy grail of astronomy as of today, at least one of the most important driving factors of astronomy, that is to discover and directly image planets around other stars. So, what is done here is using an instrument called coronagraph, you have blocked out the light coming from the star, and using a very powerful adaptive optic system which allows you to see objects which are very close to the star, and taking images with that adaptive optic system on that large telescope, you can see the planets moving around. You can see the motion of the planets around that star. So, this kind of studies are only possible on large telescopes which are equipped with very powerful what we call extreme adaptive optics, very high Strel ratio, very efficient suppression of scattering around the star, and so on and so forth. Many things have to work very well, almost to the edge of what technology can deliver today to enable these kind of studies on telescopes. So, what is the alternative? If you do not have an adaptive optics system, if you do not want to do this, you need to go above the atmosphere. So, that is another alternative which astronomers do, as illustrated here. This is the image of the James Webb Space Telescope, which is the successor of the Hubble Space Telescope. This would be launched sometime about a year from now, and it will go above the atmosphere, and it has a telescope which is of diameter 6.5 meters across, and so it is a very large telescope in space, and it will allow you to study objects in the sky without being affected by the effect of atmosphere. But the main problem with space based telescopes is something goes wrong, you cannot go there and repair it. On the other hand, a ground based telescope facilitated with an adaptive optics system can be upgraded, repaired, new instruments, new analyzing technologies introduced into that system, and all that becomes extremely difficult or almost impossible when the telescope is in space, especially it is very far away from Earth. So, and also the space based systems become very expensive. So, that is the main trade off between a ground based facility and a space based facility. Now, in addition to this space based facility which I mentioned earlier, the James Webb Space Telescope, astronomers are building extremely large ground based telescopes. I mentioned that the next generation space telescope, which is a JWST, has a diameter of 6.5 meters. However, the largest upcoming ground based facility has a diameter of 30 meter in size. It is called the 30 meter Telescope International Observatory, being built by a consortium of institutions in a number of countries, including India, Japan, China, Canada, and the United States. So, multiple institutions in multiple countries joined together, put their technologies together to build and planning to build a facility called 30 meter telescope. Again, most probably on this Mauna Kea, the mountain called Mauna Kea. This is a SolidWorks model of the telescope. This size is 30 meters in diameter, almost the size of a small football field, and this is the primary mirror of the telescope, made of about 500 hexagonal shaped segments arranged together to form a surface which is of 30 meter diameter. Light arrives on the telescope from above, converges, goes to the secondary mirror up here, and continues to converge and comes down, and there is a tertiary mirror here which bends the beam and diverts it into one of these instruments on these two side platforms on the telescope. And on these side platforms, there are a variety of instruments called such as spectrographs, cameras, imagers, polarimeters, etc. located, which work at different wavelengths, all the way from UV, visible and to up to infrared, which will allow astronomers to study celestial targets in a variety of ways. So, this as I mentioned, this observatory is being built by a large number of institutions around the world. They share the overall construction effort, as illustrated in this slide. The United States is building some of the segments, they do polishing, civil works, integration of the instruments, etc. In Japan, the telescope structure is being built, the optics for the telescope, primary mirror, the mirror blanks are being built, and so on. And a large number of these activities are also happening in India. I will show a couple of slides which highlights this. Similarly, in China, some of the laser systems, the tertiary mirror segments, instruments, etc. And the Canadians are building the enclosure for the telescope, the adaptive optics system parts, and some of the science instruments. So, I just highlight here in this slide what the Indian role is in this facility. One of the primary mirror segment is shown here as a hexagonal segment at the gray part at the top. Some of these segments are being built in India. Out of the 500 odd segments, about 100, close to 100 segments are being built in India. These segments have these segments have to be all aligned together to form a single mirror surface to an accuracy of a few nanometers, and this has to be done in real time. So, the relative positions of these mirrors have to be measured in real time, and that is enabled by using what are called these edge sensors. So, these edge sensors hang from the edges of the mirror segments and allow real time measurements of the relative positions of the segments, and those sensors are being made in India. There are then these actuators which correct for the positions of the segments, so that they remain in phase with respect to each other and form a single surface. So, all these actuators are all being made in India. This entire complicated optomechanical assembly on which the mirror segments are sitting and supporting the primary mirror, these segment support assemblies are all being built in India, and as I mentioned, a subset of a few of these segments, about 100 of these segments out of the 500 or odd are being built in India. So, a lot of activities being carried out in India to build these observatories, which form the heart of the 30-meter telescope program. Why do astronomers want to involve in such large facilities? Why do they want to build such large observatory facilities, join together with astronomers across the world, and make systems which are so complex and difficult to build? And this is driven by our curiosity to discover the universe which we live in, and the number of questions, number of fundamental questions you would like to answer. For example, if you use the Hubble Space Telescope and look at this galaxy, this is the level of detail you can see, but the level of detail which can be seen from the 30-meter telescope of the same galaxy is this. So, you can compare the difference between the best images a telescope can deliver today from space to that a 30-meter diameter telescope can deliver when it is built. So, this allows you to study this celestial object in exquisite details. What are the causes of these structures? What is going on in the middle? Is there a black hole up there? What are the star forming regions? Where are these bright arms? And how far away do they spread across the galaxy, and so on and so forth. All kinds of questions you can ask. So, TMT its dramatic increase in the collecting area and spatial resolution will lead to a revolution to the studies of many things, such as when did the first stars form in this universe, when did these galaxies get assembled in this universe, are there extrasolar planets, can we image them, can we see if they have atmospheres like that of what we have on Earth, are there rocky planets, how far away are from their parent stars, all these questions. Is there evidence of life on those planets? What is dark matter? What is dark energy? All these kind of questions can be tackled by a TMT class facility equipped with adaptive optics and very complicated instruments like spectrographs, polarimeters, etc. So, let me skip this, I mentioned all this. So, what we are trying to do here is to understand what is the discovery space in astronomy. So, one way of understanding it is to see with a suite of instruments and a telescope like this, what kind of angular resolution can you get, what kind of wavelength resolution can you obtain, and are they enough to study all classes of objects in the sky. So, if I do that kind of exercise, very often you end up finding holes in the parameter space as illustrated here. For example, if I look at objects which change its flux and its mass or brightness on this axis, you find a lot of objects in sky which are occupying this space. They change slowly in time and they have a range of brightnesses. But why are there no objects in this part? Why are the objects not changing very fast and have any of these masses? The primary reason we can't find these objects is because you do not have telescopes with apertures large enough to collect enough number of photons to study these objects which are changing very fast. So, you need a large telescope to study these objects. So, that is why you want to build a big telescope. So, by plotting diagrams like this, you can then understand what kind of parameter space your telescope needs to be designed to tackle to study new kind of objects in the sky. So, that is what is going to happen with these telescopes. As we see today, our universe, we understand, is made of large clusters of galaxies which form filamentary structures embedded with large voids where there are no galaxies. This is how we understand our universe looks like as of today. But what is important to notice here is all this visible matter you see here is only a tiny fraction of what we know is the constituent of our universe. It is only 4%. The remaining 96% of the universe is constituted by what is called dark energy or dark matter, which we do not know what they are. And TMT kind of telescopes will allow you to address these questions and try to find out what these objects are. So, to summarize, we are poised on the verge of a revolution in astronomy with a large number of new facilities being built around the world, both operating from space and from ground. And these facilities will allow you to ask and answer maybe some of the most fundamental questions you can ask ever, like how and when did the universe come into existence, is this entire universe we live in, are there other universes like this, how did galaxies take birth and evolve into what we see today, why did these galaxies assemble into this large scale structures of clusters of galaxies, superclusters of galaxies, all arranged into filamentary shapes and so on. So, what is really the large scale structure of the universe? Is there stuff we can't see like dark matter? If so, how much? And what is dark energy? Is there life anywhere else in the universe? What are black holes? How do they live? How do they take birth? How do they live and die? All these questions can be tackled by future facilities, and it is going to be astonishingly interesting future in astronomy as we go. And all this is going to produce a large amount of data. So, people who can deal with large amount of data and churn results out of chugging through large amount of data is enormously important in all fields of astronomy in future. So, data scientists are required. So, as I said, what is in store is beyond imagination. We know why we are building telescopes, look at parameter spaces and design telescopes to look for known unknowns. But what is really important is not to tackle those known unknowns, which of course these facilities will do, but keep an eye open for discovering the unknown unknowns. We can't even imagine what they are. We can't even think of them now. Those are the ones which are going to change our worldview, change the way we believe our universe is, and change our worldview perspectives. Thank you very much.